Hi, welcome back. This is homework 4, part D, and here we will be generating synthetic data for the response of our process transfer function GP, which here is 1.5 over 7s plus 1 cubed times 12s plus 1 squared, and we will have a step change input of magnitude 1.2 over 50 time steps of 2.5 time units, and then we will then add some Gaussian normal distributed noise with standard deviation of 0.05 to our calculated response. So going into our code here for part D, we can start with defining our GP is going to be equal to, go back here, it's going to be equal to 1.5 over 7s plus 1 cubed. So we can go 7 times s plus 1, and this is going to be cubed, and then we're multiplying that by 12s plus 1 squared times 12 times s plus 1 squared, parenthesis, and then we can go ahead for GP to take a look. So here is our process transfer function. Now we can go ahead and run our simulation for this system here, in which our system is the GP. Our U here we're going to call our lambda function for our anonymous function, lambda t, with time steps of 1.2 over 50 with 2.5 time units. So 1.2 comma 50, and then 2.5 time units. And then we can go ahead and call our time and our y and set that equal to our sim, shift enter, and then we can go ahead and plot this out. So we go fig is equal to make subplots, and fig dot add underscore scatter is equal to our x here is going to be time, our y will be y, and in the mode here we are going to want this to be markers, not lines, and we want it to be markers due to the fact that this is not our true data, this is what we are trying to fit. And then we can go to fig dot update layout. We can make our width equal to 800, our height equal to 600, and then our template we can use C1. Alright, so now we can hit shift enter and plot this out. So here is a plot of our data. So now what we want to do is add some noise and add some sort of randomness to our plot. So below this, we can define our y model is going to be equal to np.random, and we want to add a normal Gaussian distribution to our y with a standard deviation of 0.05. Shift enter, and then we can add this plot in. So we go fig dot add underscore scatter. Our x is again going to be t. Our y here is going to be the new model with the Gaussian distribution, and our mode here is going to be equal to lines. Or we want to keep this markers because this is not our fitted data yet. We are just adding the distribution. Shift enter. So you can see it's starting to add some noise to our system here, and it's deviating from our original response. Alright, so now that we have that done, we now want to fit a first order plus time delay model to our synthetic data in which we had created in the previous part by minimizing the sum square error between our model and data utilizing nonlinear regression. So the first thing that we can do is we are going to need, actually we don't need to because it's right here. I was going to bring in our minimize function, but I already have done that. We can go ahead and add a line of code in here. And we want to define our first order plus time delay. And within our parentheses, we want to call for our time, our k, tau, as well as theta. And then next we're going to want to return np.where, and we are going to want to return where our time is going to be greater than theta, as well as k times 1 minus np dot exponent of the opposite of our time minus the theta value, and then this will all be divided by tau. Lastly, in here, we will need to add we want our array to be like 0. We hit Shift Enter, and then adding our next line of code, we will want to define our function for our sum squared error. And within our function here, we can define a vector, and then we will want to unpack our vector in terms of our Ka, tau, and theta, and then this will be equal to our vector in which we are defining in our function. We are going to want to return our sum squared error, so np.sum of our y data, in which is using our normalized transfer function without the noise being added. So we are adding y minus FOPTD for our first order plus time delay, and then we will call our tau, Ka, tau, theta. This will be squared for our sum squared error. Shift Enter. And then the next line of code here, we're going to want to minimize this response. Doing so, we can write that Ka, tau, and theta is going to be equal to minimize, and we are going to call our sum squared error function. And we will need to supply some initial guesses, and for this we can use 1.8, 30, and 15. And it is important that we are calling values that will be somewhat close to our system in order that we are fitting, and we are going to want to call for just the x values that come from this. Now then we can hit Shift Enter. So that ran smoothly. So now we want to take a look at what these values are. So we hit Control C, Control V, Shift Enter. The minimized values for our Ka, tau, and theta. We can now go ahead and define a new y variable, and we can call this y model for our modeling data, and we are going to want it to be our first order time delay with t, Ka, tau, and theta. We can hit Shift Enter, and then we are going to want to add this to our plot. So we can go fig.add underscore scatter. X is going to remain time. Our y here is going to be y underscore model. And the mode for this will indeed be lines now, since we actually have a modeling data, and now we want to compare it to our original plot. I'm going to go ahead and hashtag this out just so that we are plotting the y data in which we had added some random distribution. So let's check this out. Shift Enter. All right, so there we have a nice fitted line to our original process transfer function in which we had simulated. Alright, so next we will move into part D3, and we will be using the fitted parameters that we have in part D2 in the calculated PI controller parameters by Smith and Corripio from 1997, and then we will simulate this closed loop response of our system to a step change in setpoint. I have already imported the PI controllers by Smith and Corripio into our code, as they are right here. So next, well, first we have our PA term, PB, IA, and IB. So moving into the process here, we will define K is equal to KA over 1.2. And then we can define our Y, and that is going to be equal to PA times theta over tau. And this will be raised to the power of PB. We can define that our Kc here is going to be equal to Y divided by K. And then next we can define our reset time, our tau I, and that is going to be equal to tau divided by IA plus IB, and then this will be times theta over tau. Shift Enter. So now we want to define GC for our controller, and that is going to be equal to KC times 1 plus 1 over tau I, and then this tau I will be multiplied by S. All right, so now that we have our GC defined, we can go ahead and define what our closed loop will be. So we can say our loop for part D is going to be equal to GC times GP, and then this will be all over 1 plus GC times GP. All right, then we can Shift Enter. So now we want to run a simulation for our closed loop transfer function here, and this is going to be our PID controlled. So we can, instead of just using T and Y, we can call these our CT and CY, just for our controlled time and our Y values. And this is going to be equal to sim. And we are going to be simulating loop D using our anonymous function lambda. We call our T with time steps of 1.2. And then we can make our N here equal to 1,000 with our time steps being equal to 1. All right, Shift Enter. And now we want to generate a plot to see how this PID controlled response works using the Smith and Corripio parameters provided above. So we go fig is equal to make subplots, and then we can go fig dot add scatter. Our x is equal to CT, y is equal to CY for our controlled, and we will use lines, updating our layout with 800, height 600, template Seaborn. Close that off, hit Shift Enter on this bad boy. All right, nice. So you can see our initial response is slightly going above our set point, reaching almost 1.28, and then dipping below to 1.12-ish, and then is remaining at a steady state. We can extend our time steps here. It's just to prove that it is remaining at this value. And we can also change this value, and we can determine if it is true, and it in fact is. So using this method and these parameters for the PID controller, we can basically set any set point, and we will result with remaining at the steady state. Thank you for watching.